much for the introduction. Good to see the spirit of so many people in the morning after a very nice dinner last night. So today I'm going to talk about the lithium and particularly related to its evolution in red giants, because the stars are basically sinks of lithium, but then there is a puzzle which was there for more than 4 decades, and then we pursued that with my students. So then we found some very interesting results. So basically, I'm going to talk about lithium, and then you must be all knowing about what is the lithium. And the lithium is, third element in the periodic table. And then basically, we look at high-resolution spectra, and then analyze them, and then quantify the lithium amount with respect to hydrogen. So much of the credit goes to my students. Bharat Kumar is a faculty now at IIA, and Raghubar is in China, and Deepak is in Aries. Anohita Malik is currently doing with me PhD on this subject. So as you know that the lithium, along with hydrogen and helium, has a primordial origin, and the basic reactions, you know that, and that's the beryllium plus neutron, and which gives the 7 lithium. This is in the Big Bang nucleosynthesis. These are the 12 reactions which define that. And then lithium normally we expressed in the stellar abundances relative to hydrogen and normalized to 12, so that then we have a much better understanding number. So on logarithmic scale, I just give you the number. You can see the primordial lithium, the current, the state-of-the-art BBN models, and then with certain parameters like, baryon to the photon to baryon ratios, which came from Planck and things like that. Those are some of the experimental values. This is the best value now. We have 2.7 primordial value. And then on the other hand, you can see on Earth, that's a 3.2, which is similar to, came from natal clouds, like interstellar medium, that's this amount. And then on the other hand, on the sun, you can see it's a main sequence star, which is almost like, 2 orders of magnitude less than what you see on Earth, or even in the ISM. It's 100 times less than. That's what it is, the logarithmic scale. So the cosmic lithium problem, we can see the prediction of light elements with eta as a free parameter. You can see here, this is the helium one, and then the deuterium, and then 3He. They all came from the Big Bang nucleosynthesis. And this is the lithium. And then the baryonic to photon ratio is a free parameter here. Once that parameter is fixed, and then you can see that this is the one where the observations show, and then the helium observations are perfectly matching, and then the deuterium are perfectly matching, helium match. On the other hand, there is an issue with 7 lithium and the BBN, the predictions. And that's called the cosmic lithium problem, which I'm not going to too much talk about that. And then you can see as a factor of 4, the difference, which is quite significant. That is still a problem. So what I'm going to talk about, something related to lithium evolution in the galaxy. It doesn't matter which I can take, either BBN model, or there is an observations which we all believe that that's a primordial value, because many of the old very metal poor stars have a very less scatter across large range of metallicity that we think is a primordial value. Actually, that is in the logarithmic scale, the 2, which is a factor of 10 less than what is kind of, a factor of 6 less than the BBN model. On the other hand, if you take, the BBN as a 2.7 or speed plateau as a 2, and then you can see the ISM, the lithium is 3.3. So basically it is increased, either whichever you take it, either observational or BBN model. If you take observations, it's a factor of 10 more. If you take a BBN, it's a factor of 4. So it doesn't matter which you take, the lithium is enhanced over the years from the Big Bang to the current value. So that's what I would just want to say. And what are the known sources? Known sources, one of the Spallation reactions, that galactic cosmic rays. And then, of course, the stars, there are, the people suggested stars also can produce The major thing is stars do produce, but then bringing them out is extremely difficult because lithium get destroyed very fast in the stars. And lithium synthesis and depletion of stars, you can see the problem here is that lithium can be produced within the hydrogen burning cell, and then bringing them is extremely difficult because the beryllium get produced at something 10 power 7 K, and then that can immediately go to the lithium here, but the problem is then the lithium get destroyed at much lower temperature. Bringing this beryllium, you have to bring the beryllium to outer atmosphere where it is cooler, and then that can transform into the lithium. Then we have to bring to the photosphere. That is the tricky, those are time versus temperatures. That is an issue. That's the way the models we didn't have. So everybody thought the lithium stars are sinks of lithium. So little bit on this, you can see these are the main sequence stars. Basically, in astronomy, basically, if you are doing stars, everything you represent with called a Hertzsprung-Russell diagram. This is the luminosity, and this is the temperature. Is a proxy to the temperature. Is a color. You can also. So most of the stars stay here, much longer time, and then the stars evolve. This is sun, then become subgiant, and then a lot of convection happens, and then the stars go in the red giant branch, and then they come down. This is called a clump, and then again they go back here. This is called asymptotic giant branch stars. Depending on mass of the stars and compositions, they go here and then end up as a white dwarfs, mostly in the low mass stars. And these are the chemical reactions which happen. The 4 hydrogen nuclei fuse together and become the helium. And through these kind of reactions, in between, in the stars, what happens is now when the stars is going up, and basically you decrease in carbon enormously because the 12C goes into 13C. And then the 12C by 13C increases, that is 13C, because 13C increases. And then increase in the nitrogen because of this one. The 14 nitrogen increases. But then the total C plus N is constant here because you don't have a fresh carbon or fresh nitrogen because you are not fusing helium triple alpha reactions. So this is a catalyst basically to fuse 4 hydrogen atoms into 4 the helium nuclei. So what the standard models say, even the current state of the art models, and normally, if you assume, and the main sequence stars something like ISM value, the way it is, and then once you go to the red giant branch, and then 30 to 60 times less lithium. That's what all the models tell us, depending on the mass. And then the convection, because of the convection, and then you have a ratio of 12C by 13C on the main sequence 90, that becomes 15 to 30 when you go to the red giant branch stars. Because of this convection reaches the hydrogen burning cell and brings the byproducts of hydrogen burning cell onto the photosphere. That's why you see these numbers. But actually, these numbers are much, much, much lesser than what the models even predict. So that means, for example, when I make the observations of Arcturus, a typical K giant, a bright giant, and you see the lithium is much less than what even the predictions say. And similarly, when 12C by 13C in many of the stars, most of the stars reaches equilibrium value. So there is some problem there within these models. Again, lithium is not necessarily the ISM value on the main sequence. Many stars differ the value. For example, the sun has much, much less lithium than what is the ISM. That itself we don't know whether it is during the pre-main sequence itself is got destroyed quite a bit. So little bit about, I want to just talk about something details here. I don't want to bore with that. So while stars are going, there are 3 main incidents happen for the star like a sun. One is here, it's called the first dead jump. Here is the place where a lot of hydrogen burning products come onto the surface. And there is another one, it's a small thing. When you make observations, you understand that. This is called luminosity bump. And here, stars stay for longer, maybe 10 to 100,000 years. That's why when you make observations of similar age, and then you can stars get clustered here. So they just go up and then come back. I don't want to go into details. And then after that, stars continue to go up, and a lot of convection, very deep convection. and then the entire phase gets terminated here. All the low mass stars undergo, they develop degenerate helium core, electron degenerate core at the center, and then a thermal runaway happens here because of the continued pumping of helium ash onto the core through hydrogen burning cell. So here is the one the helium ignition starts, and then since the helium ignition starts, there is a called, adiabatic expansion happens, and then suddenly the gravitation, overcomes the radiation pressure because hydrogen burning cell energy comes down, and then the radiation pressure is lesser, and then it shrinks. And then the star of something like 50 to 70 solar radii becomes 15 to 20, and then suddenly it drops here, and then this is called a red clump stars. There they stay for 100 million years, and then people say, the models indicate, suggest that this entire conversion of degenerate core into helium core burning at the center takes around 2 million years, but we don't know exact stages. This is just I wanted to give you, though the formulated this entire degenerate core is to 1962, we don't have any observational evidence exactly that is one is happening. There's no observational evidence because the degenerate core, that the helium flash, first helium flash, the prediction is it produces the energy of a billion times more than the sun. But where the entire energy is going, we don't know, okay? The fraction of whatever. So the most of the energy goes to remove the electron degeneracy there, and the rest only partially goes into lifting the hydrogen burning cell outside, and that's where it gets cools, and then the star shrinks, and then because of it shrinks, and then the luminosity also falls here, size and luminosity both. As you can see almost like 1.5 in the logarithmic scale, 20 to 30 times less luminous stars. I'm not going to. So these are observations now. What we are looking at it is observations. We can see now, this is the lithium I'm plotting, and then this is again temperature V minus V, the proxy to the temperature color. And then you can see all this, on the main sequence, these are all very metal-poot stars. You can see, I said the observational peak plateau is the primordial value, around 2.2 here. And then the first dead jump happens, and then suddenly lithium comes down here, extremely. For some time, the convective cell recedes from the hydrogen burning cell because of the temporary discontinuity with the hydrogen protons availability. Then something is happening here. You can see this was not there in the standard models. And then you can see the cluster of few stars here. Normally, you can see many more stars. This is exactly the place that is called the luminosity bump is happening. Stars are reversing. And this is the where it looks like it seems hydrogen burning cell moves upwards, and then it accesses a lot of protons from the cooler regions in the convective envelope, and star for temporarily cools down in the energy-wise, and then the size also decreases, and then suddenly it falls down here. That's why they stay here for a longer time. On the other hand, this is the place where extremely less lithium, and 12C/13 is so low. And this is where now recently models that extra mixing is happening. So there are various models for this, how the extra mixing is happening. So basically now you should see observations and theory says you should not see lithium. The basically is mostly get destroyed. So that's what it all says. You see the observations clearly says, and then the theory also says the similar. But then the puzzle is, in 1982, 4 years ago, you can see this is one of the lithium normal star, KJN, and then you can see one of the lithium line, that is 6707, a resonance line. You can see a very strong line, and which has abundance of almost 3.2, that is interstellar value, and which is almost like a 100 times more than what even nominal theoretical models predict, and much more than average lithium abundances in RGB stars, maybe 1,000 times. So that was but then there was not much follow-up on that. And then people thought there's something is happening. So there was a review in 20 years ago, and then they collected various in the literature, and then they had something like 2 of them. Again, they are very near the bump where extra mixing is happening, which is depleting the lithium. So just a couple of super lithium-rich stars, and then again, then a lot of theoretical models came up about how you can produce lithium during the luminosity bump. So we asked the question, okay, before that. So I was doing something else. So And then this happened to be in one of my samples. Everything looks like perfectly normal star. There is nothing abnormal about this, except the lithium line. So then we looked at it, and then where it is, what the spectral classification is, a completely red giant. So I looked at it carefully on these things, and then it has infrared axis, and then of course it has a slightly larger velocity, rotational velocity. And that time people were talking about, yeah, planets already discovered, because planets also plunge into the stars, and then planets induce angular momentum. And then since planets are so small, the lithium is not destroyed by the time the Earth, then that requires a large amount of lithium. So maybe, large amount of mass has to be thrown into the convective envelope to see this increase. So there is an infrared excess is there. The plunging gives you some kind of infrared excess. The dust throws out, and then there is a higher velocity gives you, angular momentum. So that perfectly fits. So, but then we were not sure about that. Then we looked more carefully. So these are the theories earlier. No, lithium was not basically getting destroyed. It is preserved from the ISM. But that was not, that was ruled out because there's a huge convection in the stars. And then planetary white dwarf engulfment, there's a planet engulfment. So this is one of the theories still there. And then nucleosynthesis and mixing inside the stars. And then we took up a survey. I had a very good student, the Kumar. And then getting a high resolution spectra is extremely difficult. It takes each star, even now, star by star we had to do. It takes 30 minutes to 1 hour on bigger telescopes. So since we didn't have the spectrographs here, high resolution that time, and then what we did was, let us do with the low resolution how to get these things. So we chose some 2,000 stars spanning from the bottom of this evolution, like a first dead jump, all the way to the up, and then thought of looking at these number of stars here. So amazingly so this is a technique we used because this is the first time we used, that time there was no surveys. We used, there is one lithium line and with calcium lines with extremely low resolution spectra, and then we use the ratios because these lines are insensitive to the temperature because both have a lower excitation potential as a 0, and then we look at the only similar metallicity because the calcium is the metal, and then lithium doesn't care. It's not a function of anything, It is sensitive to various things. So we used this technique, and then what we discovered was we found almost 6 or 7 super lithium rich stars, and then some of the lithium rich stars. What you found is, amazingly, at particular luminosity, this is a peaking. All the higher luminosities are something 1.6. The problem came is, then we made a suggestion, this cannot happen at the extra mixing is happening, luminosity bump, because this is the same place where extra mixing is happening, lithium is getting destroyed, and the same place you cannot bring the lithium up, such high amounts. And then even if you bring it, so basically you can't bring it. This is the hypothesis we made in that paper, 2011 with Mike Kumaran. Then again, we followed up, but then we don't know how to solve that problem. How can a place which was identified for very low lithium and then can be also source for the high lithium, that's what. Getting the spectra, you can solve this problem if I have a bigger telescope, better resolution spectrographs. I can go to much globular clusters, very faint globular clusters, I can solve this problem, but then it is extremely difficult. Then the boom came because astroseismology, that Kepler data released, and then they could see the difference between the stars, between RGB stars and RC stars. What I'm saying is RC stars is helium core burning stars. That is after the helium flash. The stars are after the helium flash. RGB stars are on the way, is ascending the RGB phase. In this case, helium is inner to core. Only hydrogen is burning. And then in this case, the helium is also burning at the center. Hydrogen is also burning in the shell. Okay? So you can nicely differentiate using the G modes and then P modes, the frequency versus spacing between oscillations. And this was a very nice thing. So what it solved the problem was, suddenly we found 2 stars which are unambiguously, these are red clump stars, and they have a super lithium rich. This is one of the first evidence we got there is something which is, nothing is happening on the red giant branch. There is something after helium flash. Still, we didn't know, really the helium flash is the one which is causing this entire thing. Then another survey we took, this time we used some survey. That survey became available in 2016 or 17 in the Chinese Lamus. Again, low resolution survey, large number of stars with the fiber. And we found 30 of stars really very high super lithium rich. None of them were on the red giant branch. So we continue with that, and then this is the first evidence we published in Nature Astronomy. And then so the lithium enhancement is ubiquitous among red clump stars. And then we also demonstrated the lithium only depletes on RGB phase. So that was one of the key. And then, so far in the last 40 years, the nomenclature for any lithium rich stars more than 1.5 doesn't apply here. It is actually minus 0.9 dex. Any star more than that, it is a lithium rich. So I'm not going to go. So we even set the evidence too, and then we set the upper limits within that time. The ignition phase started, maybe 1.5 million years or something, and then the entire thing is happening. So these are some of the more, these are the flashes, which you can see that the major flash, and then the next flash, next flash. I'm done. So based on this, we put some time limits on this. Okay, I'm not going to the evidence 3, but then I just wanted to say that now the helium flash is the one which is producing lithium, but now inspired by this, now more than a dozen papers, theoretical papers came out, and then we had to see which one really is working on that. So, and of course we need to actually come up with some quantification how much this lithium is contributing to the galactic chemical evolution, so that we only. Another thing is none of these stars show infrared excess, so we don't know what's happening there. So, thank you very much.
I guess there are no questions, but I would like to ask you, when you are modeling all these things, how accurately you have this nuclear reaction cross-section which goes into the modeling for all these?
BBN modeling, we don't do. Okay. We just take them granted. Of course, there are a lot of uncertainties in those reactions. For example, a lot of people say now 2.7 must be much less if you allow that beryllium into the beryllium reaction. So it may not be 95% or even 85%. If you reduce it, that BBN things comes down. So
what I meant is that there is no unpleasant surprises coming from basic nuclear data into your, observation which shows some,
It doesn't observations because you have seen the entire thing, because you're just seeing what it is there. You don't see 1,000 stars, you see 1 star. There is some problem there. So you are trying to explain.